So good afternoon, everybody, and good morning to those who are in the AM yet. Name is Fabian Garcia. I'm going to be presenting what we are proposing for the hindcasting of Rubble Mound. This is in conjunction with the StormSim development team, which will show the members at the end of the presentation. So hopefully this thing changes slides. There we go. So for today, I'm going to be covering like a brief introduction to build upon what Tanya just explained earlier on. Then we're going to go a little bit into detail as to the hindcasting framework, which will cover a little bit of StormSim and CHS and what they are and what they do. We'll follow it up with a little brief summary as to where we're at right now and what we are working on under this effort. And we'll close it up for some questions at the end. So as Tanya was mentioning, there is a lot of infrastructure on the or Rubble Mounds throughout the U.S. And present practice is based around the use of empirical equations, and those are used to predict damages, but have not necessarily been fully tested around a full range of variations of water levels and waves coming from incoming storms. So this effort is seeking to sort out the issue of providing guidance for Rubble Mound design and performance metrics based around limit states and confidence limits, while leveraging the use of probabilistic frameworks that have been developed under the StormSim umbrella while using CHS data. This really is meant to make the user's life easier when dealing with these types of data sets and trying to do probabilistic analyses. So having said that, there is great potential in this work unit and the development of these tools for collaboration with our district partners and subject matter experts. So I'll be gladly accepting feedback from any of those interested in considerations that you would like to include in the hindcasting framework, any knowledge of additional databases that might exist that we are not aware of, or even district projects that could be potential candidates for the type of framework that we're going to be proposing here today, which would be a data request from our side. So going a little bit into more detail as to what the proposed framework is, there are 5 main steps in this framework, starting with the structure selection process. This is where we're going to be defining those baseline metrics to determine if a protection system can be evaluated. So part of this process is determining if we have the necessary data for us to be able to process said system within our framework. Then once we go and determine that it is a viable system, we go ahead through the process of extracting the structure metrics from the provided data sets. The intent here is to leverage LiDAR data sets or field inspections that are available for us to get the best idea possible of what's the current state of the structure and what was the damage that has been experienced by said structure. Then we go to the next step, which is to develop the hindcasting storm suite, meaning what are the forces that are going to be acting upon said structure. The idea here is to come up with something that's representative enough to be able to match against the level of damage that's being perceived on the structure. Then once we set up that hindcasting storm suite, we can go ahead and actually model the structure response. This is where StormSim comes in. The idea here is to use StormSim to model the progression of damage on Rubble Mound structures across the US and try to correlate that with whatever data records we're able to find for the system. And finally, once we finish up modeling the structure responses, there's obviously going to be in-depth data analysis of the results. So we're able to spin up the best practices guidance on coastal structure design when we're talking about using the probabilistic methods that are provided by StormSim. So the first step on the structure selection, I like to use this image. This was shared by Charlene. But it highlights the location of 1,000+ rubble mound structures that are managed by the USACE. This includes breakwaters and jetties. So in an effort for us to be able to allocate priorities, as to what system can get analyzed first, besides the obvious need that there is in the Great Lakes, is going to be hinging on that availability of data, right? So the main interest of this work unit is to be able to get LiDAR dataset surveys. So we're able to characterize the damage that has been experienced by the structure throughout the different years of operation. LiDARs are good enough in spatial resolution that they are a viable option to do these types of hindcasting analysis. But I am aware, or the team is aware, that there are also other maintenance records out there, like field inspections or even published reports like the repair evaluation, maintenance and rehabilitation reports. There's an example image on the lower right corner of the slide of the type of information that you can get from these REMA reports. This is for a specific system on Arecibo in Puerto Rico. But you can see how the level of damage is highlighted by the change in elevation and the loss of materials. And they also come accompanied with some technical descriptions as to what could potentially have caused it. So it's not the best thing, but it is something that we can go off from and could leverage in the analysis of the results. So very important that, again, the analysis that we're proposing here is very dependent on the frequency and the available data that we can find for the system. So on to extracting the structure metrics. This is the workflow that's used by the Jabbletext toolbox, I believe, in order to extract all the structural information from the LiDARs. So you can see here that they go from acquiring the DEM to actually distributing transects along the center lines of the structures, to then being able to identify the core components to the structures, such as the crown, the slopes, the toe, and other additional metrics that can be used in the computation of damage. This is an example of that distribution of profiles along a center line that I was mentioning. You can see for this specific system, which is a jetty and the Merrimack River, they have profiles distributed each 10 meters, and you can get the type of information that's highlighted on the bottom figure when you can see the identify key locations of the structure, and I compare it against the idealized geometry. And this really helps us characterize what's the current state of the structure and what was the response if we do have a following DEM that we can look at. This is another image just to highlight the importance of using the LiDAR data sets and the type of information that we can grab from having two different dates. In this case, you can see not only the changes in the underlying morphology of this specific system, but you can also highlight the difference on the stone material when you compare from 2015 to 2020. So this is the type of analysis that we will be looking at in terms of narrowing down the structures and determining viability of passing through our framework. So going to the Hindcasting Storm Suite, in this case, StormSim, what it boils down to is a collection of storm water levels and waves. So for the purposes of this framework, the Storm Suite will be leveraging information from the Wave Information Study, the National Oceanic and Atmospheric Administration for water level observations, and where possible, we will be leveraging the coastal hazard systems surrogate models to be able to model historical responses of storms for the regions that they are available. Sorry. The type of storm suite that we can build is going to be hinged on the type of data that we find for the system. So an example here is whether or not we have a LiDAR data set that's only before and after an extreme event. In that case, we want to narrow the forcing information that's going to be taken into account in the model to just that extreme event, versus if we're talking about more routinary inspection, meaning it's covering a range of years, then StormSim needs to be synthesized from those mentioned sources to be representative enough of the life of operation of the structure. So since I mentioned the coastal hazard system, I'm sure most of you in this call are aware of what it is, but just to give a broad overview for those who are not familiar, the coastal hazard system is a national scale multi-agency initiative for accurate and efficient and consistent quantification of coastal hazards along the U.S. coastlines. StormSim leverages the use of CHS data very heavily, given that they provide high fidelity, high resolution, state-of-the-art hydrodynamic modeling results, but also they provide the accompanying probabilistic and statistical files that correspond to these extreme events for all their regional studies. And StormSim just makes the best use of that to bring that forward to the user and being able to provide responses that they can use in their engineering projects. This is an image that I like to show when talking about CHS because it really highlights the idea behind CHS that they want to cover the full probability space and take into account all the possible variations between these types of extreme events. And I think this image really brings that forward. You can see all the different tracks that are considered for the tropical cyclones across the different regional studies. And I think it just looks cool. Oh, sorry. So a little bit more information on CHS. If you do go to the CHS website to grab any kind of information regarding the regional studies, the type of interface you're going to find is on the left top corner of the slide, where you can see a map with the safe point or nodal information being displayed there. This is what StormSim uses as a basis to form the forcing of a project. We're leveraging the use of the AdCirc SD-Wave coming from CStorm, peaks and time series files that get reported for CHS. But again, we also use those associated probabilities to the extreme events to be able to bring out the full probabilistic nature of the process. And then on the bottom right corner, there's another example of that receival system and the type of LiDAR datasets that we're able to find. In this case, is from the NOAA data viewer for the 2016 NCMP survey that was done. So once we are able to synthesize a storm suite for the type of application that we're looking at, we can go ahead and model the actual structure response. As I was mentioned earlier, our initial approach to evaluating the structure response is going to be through StormSim. We're mainly going to be using the life cycle simulation module from StormSim to take a look at the responses of run-up, overtopping discharge rate, and armor stone damage progression for the Rubble Mound. For those that are not aware, damage progression is a model of S, and it's based as highlighted on the right side of the PowerPoint as in the CEM. And then additional modeling that is external to StormSim, for example, if we need to transform waves to the toe of the structure or any other reason, additional model can be considered, but it will be to a structure basis and leverage where needed. So what is StormSim? I'm sure a couple of you have already been through these slides, but bear with me. So StormSim is a universal, modular, and data agnostic MATLAB functions library that is really set out to help the user and do the types of analyses that are like listed here. So probabilistic coastal structure response analyses and life cycle performance analyses, CSRM feasibility studies, flood risk management, and overall just help the user and do any kind of data visualizations or technology integrations that are needed in this type of design or evaluation environment. So far, it has been developed as part of regional studies, so we haven't really had a direct line of funding to come up with all these types of functionalities and workflows. And a really good selling point is that we have built it to have native support for CHS response and statistical data. So it really makes the use of CHS data easy and no need to worry for you to try to sort out all the correlation between the different data sets and whatnot. So a little bit of context as to what are the computational kernels and workflows that are hosted within StormSim, meaning what are the type of analysis that you can do with our tools. Looking into the response-based kernels, we have StormSim probabilistic responsive structures, or PROS. You're probably heard previous communications on this coming from Abigail Steno. We also have the lifecycle simulation a module, and also the lifecycle simulation coastal structure reliability module, which is the one that we're going to be using for the hindcasting. And then within the StormSim library, we also have availability of frequency-based kernels within the PROS workflow. On the right side, you can see a table of all the supported responses that we have currently within our software. Those include run-up, overtopping discharge rate, overtopping discharge volume, median C-side and D-side stone. We got wall pressures for vertical walls, and the same is true for life cycle responses. So now that we know what StormSim is, how do we conceptualize the project to our model, right? What does the model see when we're trying to convey all this information through it? So the reality is that what the StormSim model is expecting is highlighted on the figure on the right, where you have your protection system, in this case a rubble mound. You're going to be specifying the stone size, how heavy are those stones, the slope, the toe elevation, how high that protection system is. But additionally, we are providing the storm water level response, and also the wave height that experience at the toe. So this is in reality what's going to be computed in the back end. So you can see that depending on where the wave information that you're gathering for this analysis, the need for wave transformation from an external model might be needed. So it is a consideration we need to take into account. But other than that, the characterization of a project within StormSim can be narrowed down to 4 main components. The first one obviously being that forcing, right? So in this case, forcing, we're talking about extratropical cyclone events and tropical cyclone events. That's what StormSim has been built around. The idea here is to provide a collection of time series of events. That would be the ideal case, but it does support for peaks only. StormSim also allows the user to provide the addition of sea level rise and tides. So, and that's just another adjustment that you can apply to the base forcing of the project. Once you got that part sorted, the second component is going to be the protection system element. So, what is the actual element that you're going to be analyzing in this whole simulation, right? For the time being in StormSim, we have support for levees, rubble mound, and flood walls. And all that means is that the available responses are going to be tied to the structure type that you're using. Obviously, you don't expect to get stone size if you're looking at a levee. So all those types of considerations are already embedded within our software. The third component being uncertainty. This is a big selling point for using CHS data, because CHS data already takes care of sorting out the aleatory component of the uncertainty when using forcing information. So remember that figure that was showing that they're meant to cover the full probability space. That is what this is referring to, right? They have all the possible combinations of storm water levels to wave heights. So that's a really important component. But not only that, they also provide the corresponding epistemic uncertainty, the model error that's tied to those modeling results. So this is a really key part of the whole process for you to get accurate probabilistic responses at the end. And then finally, it ends up with the configuration file, which means, this is where we control everything within the model. It's where we specify the file dependencies. It's where we turn on and off switches that we want to occur within a simulation. So saying all that, now we have this little slide that is trying to explain the two philosophies within StormSim, right? You have the tools that are going to be meant for design, and you have the tools that are going to be meant for performance. Under this work unit, obviously, we're more looking towards the performance side of things, right? We want to do a hindcast analysis into seeing how a structure that was built in the past has performed when subjected to a given forcing. So that's why you see there's a highlighted path on in green, more towards the LCS side, right? So the first step in any of the workflows that you want to execute within StormSim is to define the storm suite, right? And there's a big sticker right there to the right saying that, hey, if you are using CHS data, guess what? The storm suite is already kind of sorted because they already have a baseline storm suite and they have the correlated probabilities tied to those events. So if you're using CHS, you kind of save yourself a step. And StormSim is set up to ingest that directly. But then if you go down the pros side of things, meaning you're going for a design, we do a pseudo Monte Carlo to account for the uncertainty component by we take the forcing and we create the project forcing using discretized standard normal distributions for each of those storms. We then compute the structure responses for each one of those storms and look for the peak response. And then finally, we leverage the use of StormSim SST or stochastic simulation technique and the StormSim joint probability method or JPM to then take the epistemic uncertainty to those responses, do the integration, and come up with the extremal distributions or hazard curves for responses. Responses in this context can be still water level, like it can be overtopping discharge rate, like it can be runout. So you get a hazard curve for each one of those structure responses, and you can establish the design thresholds per the guidance. Use that for your engineering project. Then on the other side, if you wanted to evaluate the performance of said design, you can do so with the LCS computational kernel, right? In this case, since we're doing a hindcasting analysis, we're going to be taking the deterministic route, meaning we're not incorporating any kind of uncertainty to the forcing information. We want to tie it to a historical storm suite, pass through that, our structure responses computations. In this case, we are computing responses at each life cycle at each time step, right? Because we are working with time series in this point. So that is done across the whole simulation of life cycles. And then we come up with the actual structure performance metrics, which will later be used to correlate with the LiDAR metrics that we're able to extract for a given system. But if you were to do a stochastic approach to the LCS, meaning you want to understand the variability of the storm suite that you're sampling and whatnot, you're able to do so. And during that process, we do random sampling of the extreme events per the recurrence rates of said events. And we are able to add uncertainty to those life cycles and do the same step as a deterministic, which is computing the responses and reporting out the structure metrics for performance. Let's go to the next one. This right here is a flowchart of the centralized script for StormSim, right? So everything that I've said so far is purely executed from a single .m file where the user specifies the configuration file that they want to use, and you hit run. And you can see on the left-hand side, we have those 4 key components that I described earlier on, the configuration file, the forcing or storm information, the actual protection system that I want to evaluate, and the uncertainty components that are tied to the data. That then passes through a series of steps, which starts with initializing the project environment, meaning I'm checking all the dependencies, I'm creating the folders that I'm going to parse the outputs to. Any kind of thing that can throw off the model is checked here, right? Additionally, I'm parsing out the configuration file, and that gets passed through all the other subroutines that are going to be called. Then we go to the second step, where is the actual storm screening. So if we're talking about CHS data, we're talking about grabbing peaks and time series files for a specific safe point. We got extratropical data, we got tropical data. StormSim already takes care of grabbing those H5 files and parsing out all the metadata that's contained within them, all the actual simulation results, It matches together, adds circ and ST wave results together in time, and passes all the plethora of QA/QC steps in between to end up with a neatly sorted data matrix where you can have still storm water level and the corresponding waves associated to those storm water levels for each of the individual storms contained within the storm suite. So it really makes the life of the user much easier than having to match all that themselves while trying to use CHS data. Additionally, we also sort out the issue of the probability masses. We take care of finding the corresponding probability masses to the safe point, adjusting if it needs adjustment based on the availability of the simulation results, and bring that forward in a way that StormSim can use it down the line computations. Then the next step, we create the project forcing. The only thing that's happening here is that we are reformatting or reshaping that storm information that we process in the previous step to meet the need of the specified workflow. So if I'm talking about pros, I'm taking that forcing information that I processed in the previous step, and I'm applying the normal distributions to each of those storms to get the information that I need for pros. If we're talking about SCS, it means that I'm taking that already processed storm data and I'm randomly sampling from it to build the collection of life cycles for the specified year of simulations that I'm telling the software. Then it goes to actually creating the protection system, meaning it goes to the configuration file, parses out all the relevant information, and initializes the structure object, so to speak. Then the next step is to do any kind of adjustments that we want to do to the actual project forcing, meaning if we need to add any kind of uncertainty, it's added there. If we want to add tides, we add tides at that point. If we want to add sea level rise, it's added at that point. And the intent there, is we save ourselves the need to recompute the whole QA/QC thing again because we are adding the adjustments later on in the process. And then finally, we end up with the actual computing of project responses, meaning we take all of this pre-processed information, all of the structural components that we want to process, and we run them through the workflows. And that's where we get the actual response values for run-up, for overtopping, for DM50, and that sort of information. So here are some example graphical outputs that you can get for the lifecycle simulation module, specifically the coastal Rubble Mound module, right? So on the top left side, we have there a damage accumulation plot, in this case for the sea side of the structure, and it has no repairs being applied to it whatsoever. So you can see how all the damage curves across all the life cycles are just left freely to keep growing as damage keeps accumulating over time. Versus if you look at the bottom figure, it's exactly the same response information, meaning it's seaside damage progression. But in this case, we are allowing the structure to be subjected to repairs, so to speak. And the way that StormSim is doing that is that we specify an ultimate limit state for the damage of the structure that is highlighted there by the dashed horizontal line. And whenever the accumulated damage exceeds that ultimate limit state threshold, what the model is doing is it's keeping that value that exceeded the damage and then resetting to 0 and starts up again whenever the next storm in the life cycle rolls in. So that's why you can see that across the dashed line, there are some instances where you have a pronounced peak. So yeah, what I was saying is on the bottom figure, you see the peaks that are going over the ultimate limit state. That's just indicating a life cycle exceeded the ultimate limit state, meaning the structure experienced a breach, so to speak. So you're able to do any kind of post-processing to determine, oh, how many times throughout the simulation did my structure exceed that ultimate limit state? And this is the type of information that you can get from these types of plots and data sets. But then on the top right side is a similar type of informational plot where you can see the yearly mean maximum cumulative damage. You can also see the maximum cumulative damage per life cycle. And you can see the distribution of damage accumulation per simulation year. So the way that each of these figures are computed, starting from the left one, from the first one, so we take the damage accumulation with no repairs, meaning we left those life cycles to accumulate damage freely, right? So we bin all storm damage vectors across all life cycles by simulation year. So we specify the simulation year that we want to process first, let's say year one, and we go across all life cycles and grab the whole damage vector for all the storms that happen on the first year throughout the life cycles. We do that for each year. Then what we do is we find the maximum damage of each of the storms contained within each bin, and we average those out. Yeah, well, yeah, we find the maximum damage of all the storms contained within each bin, and then we average them out, and that's how we end up with a yearly value for damage accumulation. And that's that singular curve that you're seeing on the first subplot to the left. Then the one on the middle, those red jagged lines just represent the maximum damage that was accumulated per life cycle. And then the black dashed line is just the mean of those max values. And you can see that it's very close to the value experienced on the previous plot. And then finally, on the final subplot, we do a similar thing in the binning, but instead of, but in this case, we're binning per damage level and simulation year. So really gives some insight as to how damage is progressing across all the simulation. Same thing, but for pros, again, pros is really meant to generate hazard curves. So those are going to be the type of figures that you will see here. In this case, I'm showcasing there a collection of hazard curves starting from left to right, still water level HMO hazard curves that were computed with pros, but also the structure response when we subjected the protection system to this forcing information. And you can see there run up, overtopping the discharge, and overtopping volume. On the right side is just a figure that's kind of has the intent to show how the hazard compares against the protection system that's being proposed. So in this case, the colored lines on the left side are representing the expected hazard for a given set of annual return intervals, in this case for the wave height. And on the right side, you're seeing the corresponding run-up tied to the same annual return intervals. So it's a useful way to see how the responses compare against the actual protection system itself. And then now going to the mini update as to where we're at right now with the Hindcasting work unit. So there has been a lot of development done on the StormSim library this FY. We are very near to reading the beta stage for the software, which will make our life easier when running StormSim throughout these structures. We also started work on the StormSim documentation. I'll provide more details on that later on as to how we want to break it down. The hindcasting process is currently in the structure selection stage. So we're aiming to pick 5 protection systems for which we find a good set of data sets. And the idea here is that these 5 systems that we pick out will serve as a reference point for our district partners when we do set out to keep evaluating more systems. And that way, we're able to meet the need and also get people on board on using StormSim and getting feedback as to what things could be missing for this analysis. With that, if there is anybody interested in StormSim, there are different levels of engagement in which we can collaborate. Well, the first one being obviously if you want to contribute to this work unit, we are more than happy to analyze any candidate structures that you think might be viable for this, which also translates for us to a little bit of a data request. But I think it would be beneficial for everybody. You can also sign up as part of our beta testing. Again, we are almost there, but we do want to have some level of guidance draft documents, at least if you are going to be testing the tool. There's also the route of tool improvement, meaning provide feedback on any missing components that you think might be useful to embed within our tools. It could be as simple as adding additional plots or any, up the stream reporting metrics that are missing within our tool. Or, if you really want to help us out and feel like you're good at Python, there is a starting effort to transition StormSim from the MATLAB environment to the Python environment. So if that's something that interested you, the StormSim team is always looking for interested collaborators. And finally, I'll open the floor for any questions.